Hello, this is Mrs. Ward, and I'm going to go over section 9.4, mathematical induction. So the first thing I wanted to talk about was what mathematical induction is. It's a type of proof. So what we're doing is we're looking at a series of numbers and the sum of those numbers, and we're coming up with a pattern and then a formula to find the sum. And then the mathematical induction part comes from proving that that formula will work for every single term. So I start this with Carl Friedrich Gauss, which you should recognize that name Gauss because he is one of the founders of Gauss-Jordan elimination. He was a mathematician in the late 1700s, early 1800s, and he was asked to find the sum between 1 and 100. And instead of actually adding 1 plus 2 plus 3 plus 4 and going on, he decided to look for a pattern. And he came up with a pattern that if he added 1 plus 100 and 2 plus 99 and 3 plus 98, he always got a sum of 101. And he was going to have that 100 times because he's adding 100 numbers. And then he said, well, I'm actually adding those numbers twice. So then he took 100 times 101 divided by 2 and got 5,050. So he came up with a pattern instead of actually adding all those numbers. And that's what we're doing, is showing that something like this would actually work. And we're going to prove it that it will work for not just 100, but for 200 and 300, however many numbers you wanted to add. So what we're going to do today is we're going to use mathematical induction to prove statements involving a positive integer n, recognizing patterns and write the nth term of a sequence, find the sums of powers of integers, and then find finite differences of sequences. So we've done this before. If I give you this list of numbers and this sequence, and I ask you 1, 3, 5, 7, and 19, and I ask you to find the explicit formula to write this, you would go back and you would say, well, I'm adding the same number 2 each time. So I'm going to do my first plus my constant difference n minus 1. And when I simplify this is 2n minus 2, I'm going to get 2n minus 1. And that's going to be my nth term. Then if I want to find the sum, well, the first term is 1, and that'll just be 1. To find the second term, I take 1 plus 3, and I get 4. To find the third term, I take 1 plus 3 plus 5, and I get 9. Then 1 plus 3 plus 5 plus 7, and I get 16. And when I get down to the fifth term, so that is going to be 11. No, I'm going to add 9. So I'm going to do 1 plus 3 plus 5 plus 7 plus 9. And that's a 1 there. I've already added these. Do we not agree? And I got 16. So when I go to do this, I'm just adding 9 and I get 25. And so if I were to find the sum of the sixth term, I would basically take 25 and add the sixth term, which is 11, and get 36. Now that I have these all written, I'm trying to come up with a pattern, an instant formula to find the sum. And what I notice is that if I think of this, these are all perfect squares, 1, 4, 9, 16, 25, 36. So this is 1 squared, this is 2 squared, this is 3 squared, 4 squared, and 5 squared. So what I'm going to say is my formula to find the nth term is just going to be whatever that n is squared. So that is my formula. So what we're going to do today is we're first going to look for patterns like this. We're going to come up with formulas like this, and then we're going to prove that they work. So basically what I did is I just looked at the first 6 terms and I said, hey, it works for the first 6 terms. Good enough. Well, in math, good enough isn't good enough. So we're going to actually have to prove it and not just assume it's true. So that's me doing all that. So we jump to the conclusion. Mathematical induction is a way of proving it. And there are like steps that I have to do. And I say there's 3 steps. The book says 2. I'm grading you, so you're going to go with my 3 steps. First is you're going to have to show that P of 1 is true. The second thing is you're going to assume every positive integer k is true. So that's going to be the assumption. You're going to assume that P of k is true. And then you're going to prove that k plus 1 is true based on P of k being true. So that means nothing to you, so let's break it up into pieces. So the first thing I have to do is remember k plus 1, the subscript k upon 1, when I'm looking at k, means basically the next term. That's what it means. So what you're saying is if I give you the k term and I want you to find the next term, what you're going to do is any place that you see a k, you're going to replace it with k plus 1. So here I had 2 plus 5 plus 3, and I broke it down into the 3k minus 1 plus 2, which is my first term, constant ratio times k minus 1. And what I'm going to do, and it's simplified to this. So I'm going to skip to this step here. Any place I see a k, I'm going to replace it with k plus 1. So I'm going to have 3 times k plus 1 minus 1. And when I do that, I get 3k plus 2. Well, that is my sum of k plus 1. And that's the next one. So the next on part B, any place I see the k, I'm going to replace it with k plus 1 and simplify where I can reasonably simplify. So this will be k plus 1, and then here's that plus 4, less than 6, and then in parentheses, k plus 1 squared. This simplifies to k plus 5, and then I'm going to just leave this as k plus 1 squared. I might eventually want to FOIL that out, but not right now. The next one, I have the sum of k. So to find k plus 1, any place I see a k, I'm going to write k plus 1. So this will be k plus 1 squared. This will be k plus 1 plus 1. So k plus 1 plus 1 squared all over 4. That is going to simplify the k plus 1 squared times k plus 2 squared all over 4. And that's all I have to do when they ask me to find the next term. And that's what they're doing. They have the sum of the k term. They want you to find the sum of the next term, which is going to be this formula here. Okay, and why am I doing that? Because if I assume that P of k is true, and I'm going to show, and I can base that k, that implies that k plus 1 is true. So if 1 is true, that implies 2 is true. If 2 is true, that implies 3 is true. If 3 is true, that implies 4 is true. And so on. So you have this whole domino effect, so you're always proving the next term. So this is what we talked about before. If I have the sum of k plus 1, I'm going to find the sum of the previous term and then just add the next term. So that was me when I had that 25, and then I went back and added the 9 to get the 36. It was 11 that I added. That to get to 36. This was the sum of the fifth terms, and then this was me adding the sixth term. That's what that's saying. So let's start off and do this mathematical induction, showing my 3 steps, going very slowly. So here we go. Step 1, I want to show that it works for 1. So I want to show that the sum of the first term, well, the first term is 6, so the sum would be 6. If I put in 1 here into this formula, so I have 1 times 5 times 1 plus 7 divided by 2. That's going to be 12 over 2, and that's equals 6, so that works. So getting the sum of 6 this way is I just looked up here and I added the first term. This is using the formula, because this is a formula that is going to work every single term. This is me putting in 1 and showing that it does work for 1. Then what I'm going to do is I'm going to assume that S of k is equal to, and then I'm putting in k for this n, so k times 5k plus 7 over 2. I'm going to assume that that is true. So I'm assuming the sum of the k term is equal to this. Then part 3 is writing the sum of k plus 1 as the sum of k plus the next term. So I've already found k, the sum of k. I've already found that to be this. So I'm going to put that in first. So that's going to be k times 5k plus 7 over 2. And now I'm going to add the next term. The next term, highlighter, highlighter, highlighter. The next term is I'm going to go back up here. This is how I find the next term. So this right now, this would be a of k would be 5k plus 1. I need to find the next term, which means every place that I see that k, I'm going to write k plus 1. So down here, I'm going to write 5 times k plus 1, and then here's that plus 1. And that's based on the next term. So let's do some simplifying. So I have here, this will be 5k squared plus 7k over 2 plus, so this will be 5k, that's plus 5 plus 1, so plus 6. So I've done this side. I've substituted in the sk and the k plus 1 to this side. Now I've got to do this, the sk plus 1. So I'm going to go back up to my formula, and I'm going to simplify that in a second. And I'm going to go back up to my formula here, and every place I see an n, I'm going to write k plus 1. So, which is basically that there too. So I'm going to do k plus 1 times 5 times k plus 1 plus 7 all over 2. And I'm trying to show that that's equal to 5k squared plus 7k over 2. And then I want to add these so they have to have a common denominator. This is understood to be over 1, so I'm going to multiply it by 2 over 2. I'm just going to extend that line and make that plus 10k plus 12. And that'll be over my denominator of 2. Here, this I'm going to leave as k plus 1. And then this is 5k plus 12 over 2. And here I have 5k squared plus 17k plus 12 all over 2. Now I have to make the left side look like the right side, so I have choices. I can either factor this side and make it look like this, or I can FOIL this to make it look like this. I'm willing to bet that most of you are going to rather FOIL than factor, so we'll go ahead and do that. So when I FOIL this, I'm going to have 5k squared plus 5k plus 12k, which will be 17k, and then 1 times 12 is 12 over 2 is equal to 5k squared plus 17k plus 12 over 2. So I've made the left side look like the right side. So this is my proof. So 3 steps. 1, you have to show that it works for 1, and you have to show the sum from the sequence, and then the sum by putting in 1 for the n. Then you're going to assume that S of k is true. So in place of this formula here, you're just going to put the k, and you're going to say that's true. And then you're going to say, to find the sum of k plus 1, you're going to take this sum that you just found and add the next term. To find the next term, you put k plus 1 in for there, and then you substitute k plus 1 into your sum. So let's do another one and go very slow. So here, this one, we're going to use mathematical induction to prove this. So remember, this is how I find my term, my explicit formula to find the term. This would be my sum. So the first thing I'm going to do is I'm going to prove that it works for 1. Prove 1 is true. So to do that, I'm going to say here the sum of the first term would be 2. That's based on that 2 being 2. And then I'm going to say the sum of 1 is equal to 1 times 1 plus 1. So that's equal to 1 times 2, which is 2. So the first term works. The second thing I'm going to do, let's switch colors. Maybe that'll motivate some people. Switch colors. I'm going to assume SK is true. So I'm going to assume the sum of k is going to equal, and then in place of this n, I'm going to write k. K times k plus 1. And then the last thing I'm going to do is I am going to prove, and then this is kind of like my roadmap, that S of k plus 1 is equal to the sum of k plus the next term. So now I'm going to put that in. So I'm going to actually do left to right this time. So sk plus 1, I'm going to put in k plus 1 every place I see this n. So I am going to have, whoopsie, I am going to have k plus 1, and then this will be times k plus 1, and then there's a plus 1, is equal to the sum of k, which I just said from up here. I'll highlight that, the sum of k. So that's going to be that, and that will be k, whoopsie, don't you hate it when I forget to change my pen? K times k plus 1 plus the next term. Next term means I'm going up here and I'm going to put in k plus 1 for that. So I'm going to do 2 times the quantity in place of n, writing k plus 1. So 2 times k plus 1. Now I'm going to write this, leave this as k plus 1, and then this will be k plus 2. And then, see how I have k plus 1 here? I'm going to factor that out, k plus 1, and I'm left with k plus 2. Well, that makes life so easy because I have the left side looking like the right side, and I am done. So that was the simple mathematical induction proof. Let's look at the next example. So here I have the same thing. I'm following the here's the formula. So I am going to prove that what I'm going to do is I'm first going to show that show that S1 is true. So the sum of 1, well, 1 to the third is 1. And then putting in 1 into this formula here, I'm going to have 1 squared times 1 plus 1 squared over 4. So this will be 1, and then this is 2 squared, so 4 over 4. So 4 over 4, which is 1, so it works for the first term. The next thing I'm going to do is I'm going to assume that the sum of k is equal to k squared times k plus 1 plus 1, forgot my plus 1 plus 1, plus 1 plus 1 squared over 4 is true. So assume k, and then simplifying k squared, and then this will be k plus, that's plus 1. No. Oh, wait. Hold the presses. I messed up. Let me go back. My bad. Gosh, don't you hate that? And I can't edit. So this is k squared. K squared. And then this is k plus 1 squared. No plus 1 because I'm just putting in k over 4. So I'm going to assume that that is true. Okay, now I'm back. I'm back with me. I'm good. And then the last thing I'm going to do is I am going to prove that the sum of k plus 1 is going to equal the sum of the previous term plus the next term. So here we go. In place of going back up here, I'm putting in k plus 1. So it'll be k plus 1, that quantity squared, and then k plus 1 squared, that's all over 4. And that's going to equal the sum of k, which we just wrote up here. So k squared, k plus 1 squared over 4, plus the next term. So I'm going back up here, and it's n to the third. So I'm going to write k plus 1 to the third. So here I'm going to simplify, and I'm going to have k plus 1 squared. And then this is k plus 2 squared all over 4. And then this side is going to be, I'm going to put that over 4 if you don't mind. Like this is 1. This is over 1, so I'm going to make that 4 over 4 if you don't mind. And then I am going to have k squared, k plus 1 squared plus 4 times k plus 1 cubed all over 4. Now, I really don't want to have to FOIL all these out, so I'm going to look and see if there's something that I can factor out. So I'm going to leave this side alone for right now. And I think that we can agree that I have a common factor of k plus 1. The most number of times that that occurs is this twice. So I'm going to factor out k plus 1 squared. And when I do that, I'm left with just k squared here. When I do it from, when I factor that out from this term, I'm left with this 4 and 1 k plus 1. And that's all over 4. Leaving this side alone because I really don't, well, I don't want to change it. This I have the k plus 1 squared, so that matches, so that makes me happy. And then here I have k squared plus 4k plus 4 all over 4. And when I look at this, what I have matching, so I have this matching, that matches that, the 4 matches the 4. I just got to ask myself, can I make this look like this? And I'm hoping you're saying yes, because what I'm going to do is I'll leave this as k plus 1 squared. I'm going to leave this as k plus 2 squared over 4, k plus 1 squared. And then this can be FOILed or factored as k times k. The 4 factors is 2 and 2 plus and plus. So that'll be k plus 2 squared. So I've made the left side look like the right side, so I am good. Okay, one more. So this one is the same thing, except for I'm writing it in sigma notation. That really shouldn't bother me. So I'm writing in sigma notation. Remember, this is the explosive formula. So this is just a different way of writing it. That is the explosive formula to find the nth term. This one, I'm trying to prove that this formula will work all the time when I have I times I plus 1. Same steps. First thing is I'm going to prove S of 1 is true. So I'm going to put in S of 1. So 1, sum of 1, doing it from here, that's going to be 1 times 1 plus 1. So that's 1 times 2, which is 2. S of 1 for here, putting in here, I'm going to have 1 times 1 plus 1, 1 plus 2, all over 3. So this is 1 times 2 times 3. So that's 6 over 3, which is 2. So I've shown that the first term works. The next thing I'm going to do is assume that S of k is true. So I'm going to assume that S of k is equal to k times k plus 1, k plus 2 over 3. I'm going to assume that that is true. And then the third thing that I'm going to do is prove that the sum of the next term is equal to the sum of the first, this is one term, plus the next term. So for this, sk plus 1, I'm going back up here. Any place I see an n, I'm writing k plus 1. So let me do that. So that'll be k plus 1, and then k plus 1 plus 1, and then k plus 1 plus 2, all over 3. S of k is this. I've already written it. And then to find the next term, I'm going up here to this, and I'm putting in k plus 1 for those i's. So I'm going to have, oopsie, that's a plus sign. K, and k plus 1. k plus 1 plus 1. Wait, that should be a k plus 1 there too, right? Yes. Let me rewrite that because that's really messy. That's n, and n plus 1. All right, so left side, k plus 1, k plus 2, k plus 3, all over 3. This side, I'm going to multitask. I am going to think of this over 1 multiplied by 3 over 3, so I have that common denominator. So I am going to have k times k plus 1 times k plus 2, and then this will be plus 3 times k plus 1, k plus 2, all over 3. So the left side looks good. Gonna leave it. Right side, I can see that I can factor out a k plus 1. I can see that I can factor out a k plus 2. And what I'm left with is a k plus 3. And that's all over 3. So now I made the left side look like the right side, and I am done. Okay, I think that's a good place for us to stop and for you to get some practice. And if you have any questions, we can catch up with those next class.